Welcome learners. In today's lecture, we are going to conclude the second chapter and we are going to talk about the final charge distribution starting with the surface charge density. And then we are going to look at a practical use case for this charge density, especially being utilized in the operation of a famous passive element known as capacitors. So let us begin our discussion for field of sheet of charges, or how we find the electric field for a sheet of charge. So this is a configuration which is having many names. One is to find the fields on a sheet of infinite charges. Another name associated with this is uniform sheet density, and its famous name is surface charge distribution. So this charge density is represented by the variable of rho, and we use the subscript as S. It has the units of coulomb per meter square. This kind of charge density is normally found when we consider a strip of copper or a conducting material, strip of a conducting material. Sometimes we take a transmission line cutout, or we also can utilize these field distribution on a parallel plate capacitor, where we are going to have a use case of this as well. So this is where the charges are existing. Since these charges are existing, for example, if this is a strip of copper, so since these charges are existing on the surface and not inside of these elements or materials, that's why it is famously known as surface charge distribution, with the symbol and unit of as such. So let us try to find the electric field associated for this surface charge distribution and see what is going to be the value that the electric field is going to provide us by the charges that generate those field lines. We begin our analysis by these constraints. We consider a plane that is basically a YZ plane. Since we have considered a YZ plane, and based on our previous understanding of the last topic on line charge distribution, we know that the components of the electric field along the EZ and along EY should not be present, or it should be equal to 0. So the only component that is going to be present will be perpendicular to this YZ plane, and that is going to be E of X. So the x-axis will hold its component. So now let us visualize this idea and then see how we can find the differential electric field and then later on the total electric field of a sheet of charge. So let us take the right hand coordinate system and define the coordinates. So this is y, z and x. Now let us take a sheet, an infinite sheet on the YZ plane. So which means the sheet is parallel to the y and z axis. Since it's an infinite sheet, so I'm going to put a dotted structure over here. So this is an infinite sheet. On this sheet we have following data. So the data is, it has infinite charges on the sheet. So I'm just drawing the infinite charges on the edges of the sheet, but we assume that the charges are on this sheet and they are available anywhere. So this is the infinite sheet charges. So we know that all these sheet charges or these values can be represented by one variable, that is the surface charge distribution. So these are the sources of charges and these are infinite, so I'm just going to write the infinite ranges. Now we want to see the effect of these charges that are present in this sheet. So in order to do this, let us take one point on the sheet or on the YZ plane. So I select this point. Let me take this point as the source point, and I, instead of taking the complete sheet, I'm going to take a certain portion of the sheet. Let's say I'm taking this cutout. So it is basically the width along the y-axis, so I'm calling it as d of y. So this is the cutout that I have taken. So let us go with another formation. So the cutout is along d of y. So instead of taking the infinite sheet, I've just taken one portion out of it. And the charge or the source point is lying inside this strip. And if I look at this strip, it is basically representing a line charge distribution rho of L. Let us take one point other than the YZ plane. So if I extend the x-axis like such, I can take one point over here. This is the point P where the test charge is. And now I want to study the effect of this charge onto this point, which in turn means that the electric field is going in this direction, d of E. So this is the differential electric field that is in a straight line. Okay, this is a straight line which is originating from this charge going to the source point P, and I can obviously, since this is my direction, I can say it is distance vector r with unit vector A of r. So these are the values on the sheet. Now what else we need? We need the location of the axis. So since my point is along the x-axis, so it is going to have a certain value along the x coordinates, but nothing on the y and z coordinate for point P, and similarly my source is existing along the y coordinates and nothing on the x and y. So these are the point of interest for this strip that is lying inside the sheet. And I can also correlate the line charge with the surface charge, as I know that my line charge or my rho of L is basically dependent upon the surface charge distribution and the width represented by d of y. So mathematically, I know the unit of line charge distribution is coulombs per meter, surface charge is coulomb per meter square, and the distance unit is meter, so it cancels out. This means that this assumption of a strip existing inside the charge or the sheet is valid. So this is my strip which is existing inside this infinite sheet. So now when I have selected this small strip, my analysis becomes a bit easier. So what else can I know? Whenever I'm dealing with a line charge, we always have to know which symmetry is not affecting the electric field and which components are present. So the components of the electric field E in this comes out to be, one of the component is along x-axis, so DEX, and the other is along the DEY. So later on I know that DEY is going to cancel out, only the component along X will survive. So these are the components of the differential electric field DE. So now let us write the mathematical proof for this electric field. So I know that the differential electric field for this strip line comes out to be rho of L divided by 2 pi epsilon naught. So I can say take absolute of the distance, or I can just write r for the time being along the unit direction A of r. So this is the mathematical expression for the line charge distribution that I have utilized. Now what I can do is I can replace the appropriate values. I know the line charge distribution is dependent upon the surface charge distribution and the width along the y-axis, so it is d of y 2 pi epsilon naught. And what is the value of r? This is the distance vector from the source point to point P. So the value of r comes out to be, I can write the value of r over here. So r is going to be x A of x minus y A of y and nothing on the z axis. So once I have r, I can find its magnitude and the unit vector, so I can directly put the point over here. The value of r comes out to be, or let me write the complete equations for the unit vector so it will become easy. So I'm interested in finding unit vector of r. This unit vector of r is basically the vector r and the modulus of this vector. So the vector r is having this value and its modulus is going to be r absolute, which is the square of the scalar values x square plus y square. So this is what I have for the unit vector. So my equation for differential electric field now comes out to be rho s dy 2 pi epsilon. I can write the value of, so this is my absolute r, it comes out to be under root x square plus y square, with the unit vector being x a of x minus y a of y divided by x square plus y square under root. And if I want, we can simplify the equation as well, such that my final equation comes out to be rho of s d of y divided by 2 pi epsilon naught, and since 1 by 2 becomes 1, so it is going to be x square plus y square, and the only unit vector available is going to be along x-axis, since this y becomes equal to 0. Why? Because as I have selected a strip on the positive side of the origin, I can select the same on the negative side of the sheet along dy. So this point or any point selected over here will be concentrated to the local or the focal point or the point where the test charge is. It will have its components along d of x and d of y. So this will be along d of y for the second component, and it is going to cancel the effect of each other due to symmetry. So thus I can reduce the y e of y from this equation, and the final equation for the differential element comes out to be as such. Now once we have this value, let us find the electric field or the overall effect of the electric field. So I'm going to integrate the previous equation for the differential electric field, and it is going to be from minus infinity to plus infinity, and this is along the y-axis because we have the yz plane. So the equation now comes out to be rho of s divided by 2 pi epsilon naught, this is x square plus y square, and we have x along the unit vector a of x. Let us simplify it by removing the coefficients. So rho of s can be taken out along with x divided by 2 pi epsilon naught, and then I can integrate from minus infinity to plus infinity the values of 1 divided by x square plus y square with a of x. So I can solve this integral by using the identity, and the identity is as such. So whenever we have an integral of 1 by a square plus x square along d of x, it can give me 1 by a, or I can use this equation, 1 by a tangent inverse x by a. So using this identity I can solve for my integral. So e comes out to be rho of s with x 2 pi epsilon naught, and the identity becomes, so this is basically your a and this is your x, so it will be 1 by x tangent inverse y by x with minus infinity to plus infinity. So if I solve this tangent integral, so once you have tangent inverse infinity, it comes out to be pi by 2, and tangent inverse minus infinity comes out to be negative pi by 2. So once you take the difference of these two, it will be pi. So this means this pi is going to cancel this pi, and this x is going to cancel this x. So my final electric field comes out to be rho of s divided by 2 epsilon, and then I had this vector a of x, so I'm going to write it as a of x. And we can also simplify this equation by replacing a of x, since this a of x, if we look at our sheet, is normal to the yz plane. So I can write this a of x in a generic form as a of n in volts per meter. So this is the mathematical expression or proof of the electric field along the sheet of charges. And now if we compare the electric field equations for all the charges we have found, so we come to a very interesting thing with this equation for the sheet charges. We know that the electric field for the volume charge was dependent on 1 by r square. We know that the electric field for the line charge distribution was dependent by 1 by r, and in this case the electric field for the surface charge is not dependent on r. So which means that whenever we have charges in close vicinity for the volume and the line, the charges distance is going to affect the electric field. but not in the case of surface charges, which means that whatever is the distance between the charges, if it is lying on a surface, it is not going to affect the electric field. So if we find the electric field response of a single charge, its effect is going to remain across the board. For example, if the electric field of this charge is some value, it is going to have the same value for this charge, because the distance or value of r is not included in its equation. So this is the important finding for all the three charge distributions which we saw previously. Let us now look at some of the problems associated with this to further understand how to solve these questions. So let us look at the first problem. We have charges lying in y equals to minus 5 axis in the form of infinite sheet, and we have been given surface charge as 20 nanocoulomb per meter square. We have been asked to find the electric field in all directions. Okay, so this is the first question that we want to solve. Okay, so we know we first draw this visually to get a better understand where the sheet is and which are the planes that we want to know, and how we can then solve it for the electric field. So the charges or the sheet, so this is sheet of charges, let's do it like this. Sheet of charges is lying in y is equal to minus 5 axis. So y is equal to minus 5, let us say, is this point. So now our sheet is so the point to know is that whenever your point is given on the axis, the sheet is going to be made in the perpendicular axis. Since the point is along negative y, the sheet will be existing along, so let me change the color for better visibility. So if the point is minus 5, the sheet is going to be lying along parallel to z and x-axis. So the point will be as such. This is the same thing. If you remember, we said this is equal to y equals to 0 plane, or the other name was xz plane, which we saw in the rectangular coordinate system. So this means that the sheet is along the x and z plane, and now we want to know how many charges are there. So obviously it is represented by the surface charge density having the value of 20 nanocoulomb per meter square. Now we want to find the electric field in all the direction. All the direction mean what is the electric field on the negative side and what is the electric field if the sheet is moving from this point of minus 5 to, let's say, point of plus 5. So this is the direction of electric field to this point, let's say. So this is what it means to find the electric field in all the directions. In other words, you need to find the electric field in behind and front of this plane of sheet. So in order to find the electric field, we start by just writing the equation, which is surface charge density divided by 2 pi epsilon, and what is going to be the normal vector? Obviously along AY, because the sheet is along the XZ, so the normal is along the other axis, which is AY in this scenario. So the value comes out to be 20 into 10 raised to power minus 9 coulomb divided by 2 into 8.85 into 10 raised to power minus 12 along AY. So the answer which I am getting is 11 point or 1129.3 along AY volts per meter. So this is the electric field on the origin, which is to the left or the negative infinity. Similarly, the electric field on the other side will be negative 1129.43 A of y volts per meter, because now the magnitude is the same but the direction is changed. So the electric field becomes with a negative sign for all the values on the right and left of the equation. So this is what I am getting as an answer, and hopefully you have now a better understanding the advantage of not having the distance vector involved in this equation of the electric field. Now let us solve another question. So this question is an interesting one. So we have three infinite sheet of charges, and they are located at these points. So the first sheet is having location of z equals to 4 and its surface charge density is minus 8 nanocoulomb per meter square. The second sheet is located at location Z is equal to 1 and it has a surface charge density of 6 nanocoulomb per meter square. The third sheet is located at Z equals to -4 and it has the surface charge density of 3 nanocoulomb per meter square. We need to find electric field, let's say at these points A, which is 2, 5 and -5. Then we want to find electric field at point B, 4 to -3. Then we want to find electric field at point C, that is -1, -5 and 2. So how can we go about this solution? So this is a very interesting problem. So again, as I always say, first draw the axis to get a better understanding of the question, and let's see what we can do afterwards. So let me draw the axis. So this is z-axis, y-axis and x-axis, and we have been given that the sheets are lying along the z-axis, which means that our sheet will be in the other planes. So at z equals to 4, at z equals to 1, and let us say at z equals to -4. Okay, so the first sheet is going to be along parallel to the y-axis and x-axis. So this is the first sheet. The second sheet is, let me bring point 1 a bit down, on z point 1, so it is parallel to x-axis and y-axis. The third sheet is at point 4, so it is along this point. So these are the sheets which are at the given z-axis points, and the respective values of the surface charge densities are as such. Let me call this E1. I need to find the electric field E1, E2 and E3 for these respective sheets. Okay, now the first point that we need to find the electric field is lying at 2, 5 and -5. So this point comes out to be x is equal to 2, y is equal to 5. So x will be somewhere 2, y equals to 5 and z is equal to -5. So this point is lying over here, 2, 5 and -5. So as you can see, the point of interest where the electric field needs to be found is below the three sheets. So this means that my equation is going to be what? So let me first write the equation. I need to find the total electric field, again using the principle of superposition, which means I need to add the electric field from the first sheet, the second sheet and the third sheet. So what is the electric field of the first sheet? Obviously it is going to be rho of s divided by 2 into epsilon, and it is going to be along certain unit vector. So since our sheet is along x and y, so the unit vector will be a of z. For the second sheet, it is going to be rho of s, 2 of epsilon, again a of z. For the third, it is going to be rho of s, 2 epsilon, and again a of z. So now I have written the three equations for the three electric fields, but now I need to know what is the basically point of, or the values of the coordinates. So if you look at point P, it is below sheet 1, which is located at z is equal to 4. It is also below sheet 2, which is located at z is equal to 1, and also the third sheet, which is located below z equal to -4. So this means that the direction of my unit vector will be negative, negative and negative for all the sheets. So this is the point which I wanted to emphasize on, that the direction of the unit vector along the z-axis depends upon where the point of interest is located compared to the three sheets. So once we do this, we should get a generic value of 1 by 2 by epsilon, and I can bring negative a of z as a common. I'll be left with -8 nano plus 6 nano plus 3 nanocoulomb, and the answer which I am getting is, as a total electric field effect will be -56.47 along a of z volts per meter. So this is the answer for the first part of the problem. Now let us go to the second part. The second part, we have the point now at 4, 2 and minus 3. So this point is x equals to 4, y equals to 2 and z is equal to minus 3. So this means it will be somewhere over here. So it is going to be 4, 2, minus 3. Again, you can see that this point is below sheet 1 and sheet 2, but it is above sheet 3. So my equation will remain the same, that I need to find the total electric field, which is going to be the sum of electric field from the first, from the second, and from the third. So it comes out to be rho of s 2 epsilon, again along the z direction. What is the sign? We'll come to that. Plus rho of s 2 epsilon, again along the z direction, then rho of s 2 epsilon, again along the z direction. Now what is going to be the sign in this case? We have to see where our sheets are. So for the first sheet, the point is below it. This means that it is going to be negative. For the second sheet, the point P is below the second sheet, so it is going to be negative. What about the third? So the third sheet is below this point, so we are going to write it as positive. So this is what we are getting. Again, to summarize, if the point is above a sheet, you take the unit vector to be positive, as we did over here. If the point is below the sheets, you take unit vector to be in the negative direction. So answer for this comes out to be 282.35 along the z direction volt per meter. And now I leave the third part for you, where my answer comes out to be as such, and you can verify by yourself. It is 961 along AZ unit vector volts per meter. So I do encourage you to write the equation for the third part, given that our point is now this one and it is lying somewhere around the point of -1, -5 and -2. So it is going to be somewhere over here, -1, or if we take the exact values, it is going to be -1, sorry about that, it's going to be -1, -5 and 2. So this is the third point. So you can now figure out how your equation is going to be formulated. Now coming to the last part of this chapter, and that is a case study based on the surface charge distribution of a parallel plate capacitor. So we want to see that in reality, the parallel plate capacitor, or the field that exists inside the parallel plate capacitor, is the only one that is between the plates and not outside. So the parallel plate capacitor is something that has two sheets. If we look at it from this perspective, one sheet is positively charged, other sheet is negatively charged, and the electric field is flowing from the positive to negative. So electric field is something like this, and we can verify from the surface charge distribution that electric field is only going to exist inside the plates and it is not going to be available outside of these plates. So in order to verify this, let us apply the mathematical expression on these sheets. Assuming that our sheets are something like this, they are located on y is equal to 0 plane. So these are the two sheets. Let us say one is positively charged, other is negatively charged, and this is a positively charged sheet and this one is a negatively charged sheet, and we want to find electric field that is available inside the parallel plate capacitor, and nothing is outside, or no electric field exists on the outside of the sheets. So in order to do this, let us first draw our axis and then find the relevant electric fields. So this is the axis. We have y-axis, z-axis and x-axis. Now we want, and this is the origin. So let us say that the one part of the sheet is lying on x equal to 0 plane, and the other part of sheet is lying on some x is equal to radius value a. So let us say this is at x is equal to 0 plane, and this is, let's say, x is equal to some radius a plane. So the distance from here to a is a. And we have a few points inside this plane where we want to confirm that the electric field is going to exist or not. So let us take point 1 over here, that is behind the first sheet lying on x is equal to 0. we take a second point P2 which is in between the sheets, and then we have a third point P3 which is again lying outside the x is equal to a sheet. So these are our source points, and this is the point where the test charges are at point P1, P2 and P3, and the effect obviously of the electric field should be inside these sheets. So this is what we want to find. Again, it's a YZ plane or the x is equal to 0 plane. So now let us do this analysis case by case. So the first case is that x is having a location of less than 0. This means we are going for point 1 behind the sheet. So point 1 is behind the sheet, or you can say the positive rho s sheet. So if we write the total electric field equation for this, so electric field total is going to be electric field effect from the positive sheet plus the electric field effect from the negative sheet. So let us say this is our negative sheet and this is our positive part of the sheet. So the charges here are positive and negative with surface charge values of rho of s. So we want to see the effect of the electric field. So we can see that the source point or the positive sheet will have the waves or electric field lines moving towards this point, and similarly the negative field will also have the effect moving towards this point. So the total electric field will be rho of s divided by 2 epsilon into a of x. This is the normal vector because the field was or the sheet was in yz plane, plus minus rho of s divided by 2 epsilon into a of x. Now what is going to be the sign? Since the energy is moving from the sheet to the back of the plate, it will be along negative ax and the other will also be along negative ax. So this and this cancels out, it becomes positive. So overall my electric field is 0. So this is the first case, volts per meter. So we can verify mathematically as well that no electric field or the energy is going to exist behind the first sheet. Now let us take the second case. So I'll try to keep it everything on this page. So case number 2. Now the location is x greater than 0, which means now we are talking about the third point, which is x is equal to a radius sheet. So this is the case now. Now again we want to find the total electric field, which is the sum of the positive electric field and negative electric field, P negative and P positive. So it is going to be rho of s 2 epsilon. The equation will be the same, a of x plus rho of s 2 epsilon, and then unit vector normal is a of x. Now what is the value for a of x? Since the sheet is moving from 0 towards a and it is going beyond that, this will remain positive and this will remain positive because both the sources are now pointing towards this. So this sheet is pointing towards this point and this sheet is also pointing toward this point. So the equation will be as such. In this case, our value for rho of s, don't forget this is a negative sign, so it comes out to be 0 again, volts per meter. Again the sheet was lying outside the field, so the electric field is 0. Now let's go for the final case. In the final case, case number 3, we have that sheets are lying between x and a, so the total electric field is again the sum of positive rho plus negative rho, and we are talking about point 2, which is in between the two sheets. So it comes out to be rho of s divided by 2 epsilon along a of x plus negative rho of s divided by 2 epsilon into a of x. So again we know that this sheet is going to send its energy from the charges to point P, and this will go in the opposite direction. So for the first case this will remain positive, and for the other case we are moving in the backward direction, so this will become a negative a of x. So I'll just write it, negative a of x. So these two become positive and this becomes positive. So my answer will now come out to be rho of S divided by epsilon into A of X volts per meter. So this is the total electric field effect for the third case, and hence we can prove that the electric field is only present for point P2, which is between the two sheets, and there is no electric field outside the sheets, whether if it's at location point 1 or location point 3. And this was a practical case example or a parallel plate example of sheet of charges for the capacitor.